Hello, this is part 3 of the chapter 2 lecture. Because in part 2 of the lecture, we learn what are the subatomic particles of an atom. In this part, we are going to learn about what are the numerical numbers, such as what is atomic number, what is mass number, what are isotopes are called. So one thing that we need to be sure about an atom is that atom has unique number of protons. A specific atom has unique number of protons, and those protons can be used as its identity. So as it said here, all atoms can be identified the number of protons and neutrons they contains, but specifically the number of protons an atom contains is used as its identity that we call as its atomic number. It's directly calculated from the number of protons it contains. Basically, as it says here, atomic number is the number of protons present in the nucleus. So because atoms are neutral when we find in its natural state, the number of protons contains is equal to number of electrons, because as we discussed in part 2 of the lecture in this chapter, both protons and electrons contains the similar magnitude but opposite charges. So proton contains positive +1 charge and electrons contains -1 charge. So if the element is neutral, the number of protons an atom is going to have should be equal to number of electrons the atom is going to have. So if you know the atomic number of an element, you know the number of protons the element is going to have, and if you know the number of protons the element has, you know how many number of electrons the element is going to have. So if you look at this example of nitrogen, so nitrogen has atomic number of 7. So it should have 7 protons, and if it is neutral, it should have 7 electrons. And we already discussed in previous lecture that atom also contains massive subatomic particles that are called neutrons with a neutral charge. So these neutrons will also present in the nucleus and is responsible for the mass of the overall mass of the atom. That's why we call a mass number as the collective masses of the protons and the neutrons present in an atom. So this is typically how a element symbol is presented in an atom, and its mass number and atomic numbers are presented like this. So atomic number is the smallest number you can find next to an element symbol in the periodic table that is equal to number of protons, and the largest number you can find next to the element is the mass number, where it is contains the overall masses of the protons and the neutrons present. Excuse me. So far what do we know is elements contains unique number of protons that we use it as an atomic number to communicate, and that number is fixed because number of protons doesn't change for an atom. However, the number of neutrons present in the nucleus are not used as an identity for the element, because the number of neutrons present in an atom can fluctuate. The role of a neutron, if you think about it in nucleus, is that, again, going back to Coulomb's law, similar charges repel. What we discussed in the previous lecture is that nucleus is a tiny area compared to a large mass, large overall size of an atom, even though overall they both are small. Remember that New Orleans dome, Superdome, versus a marble. That marble is the nucleus, then the whole stadium is the atom. So if that tiny is the nucleus, and if you're putting protons in it that contains positive charge, they have to hit each other and they repel each other. So to avoid that, neutrons were present because they act as a buffer to protect the repulsions between proton and proton so that they wouldn't destroy the nucleus. So inside the nucleus, you have a tiny attraction between proton, even though they were similar charge, and majorly the repulsions were minimized by the presence of nucleus. So that number of required neutrons present in the nucleus to keep the nucleus stable differ from element to element. Sometimes you have for number of protons, you have equal number of neutrons. Sometimes you have more neutrons than the number of protons an element is going to have, which we will going to discuss in the next part of this lecture. So because an element can have a different number of neutrons while it is having its own number of protons same, we call them with a different phenomena, or we give them a separate name to it. We call atoms with the same number of protons but different number of neutrons as isotopes. So isotopes are two or more elements that have same number of protons but different number of mass number because they contain different number of neutrons. Let's look at these examples of isotopes of one to each other. We know that hydrogen contains one proton, so we call it as hydrogen 1,1. However, hydrogen also contains an isotope, which means it's still an element with only one proton, so it is obviously a hydrogen, but it contains another neutron as well. So in comparison to the previous element, this one doesn't contain any neutrons. However, the isotope of this protonium deuterium contains one neutron. So mass number is different. But however, they both are same elements because they still contain same one proton. So identity is still the hydrogen. Again, it contains another isotope called tritium. So tritium contains still one proton, so it is still a hydrogen, but tritium contains two neutrons. So overall mass number is 3. So the relationship between protitium, the hydrogen, and the deuterium and the tritium is that these three are the isotopes of each other of hydrogen atom. Again, the definition of isotope is an atom with same number of protons but different number of neutrons. As a result, they have different mass numbers. Now, because we know how to calculate the number of protons, mass number, number of electrons, and number of neutrons, let's practice, right? So my expectation is that whenever I say practice is, I will show you a problem here. My expectation is that you would pause this video, practice before you see the rest of the part of the lecture where I will show you the answers, so that you will make sure you understand it before you practice. Right, let's see this problem. So problem is asking, determine the number of protons, neutrons, and electrons in each of the following spaces. Let's go by one. So what is the strategy is going to be is you're going to use the strategy that the formula that says mass number A is equal, mass number A is equal to number of protons C plus neutrons. Let's call it as capital N. We don't typically label neutron as capital N, but just for the simplicity of this problem, let's label that as. So because we already know that for a neutral element, number of protons is equal to number of electrons, you can say that C is equal to number of electrons. All right, you are simply going to use those two formulas. Now let's look into first problem. A says that chlorine 1735. So which one is going to be A, which one is going to be C? The atomic number is the smallest number available. So chlorine has atomic number of 17, so it should have 17 protons. All right. So let's identify what is the number of neutrons present. Chlorine 35, saying that mass number is 35. So chlorine number of neutrons, if you rearrange the top formula that you're seeing, it should be like N is equal to A, the mass number, minus D. So N is equal to 35 minus 17. So it should be 18 neutrons. And what are the number of electrons for chlorine 35? Because it had 17 protons, it should have 17 electrons. These should be your answers. Let's go to second problem. It says just chlorine 37. So one thing that we can rely on is a element symbol associated with certain number of protons. Certain number of protons is associated with a fixed element symbol. So if you know number of protons, you can always identify which element it is exclusively. And if you know element symbol, you can always identify how many number of protons it is going to have. So for chlorine, you can identify that chlorine has an atomic number of 17 from the periodic table, which means it should have 17 protons again. So this time chlorine has 37 as mass number. So now to identify number of neutrons, you subtract number of protons, the atomic number, from the mass number 37. So 37 minus 17 is 20. So it has 20 neutrons. Now, because chlorine has 17 protons, it should have how many electrons? 17. All right. Now let's work on the rest of the two problems. Okay. So problem C says that potassium 41. So it didn't give any atomic number because the number 41 looks like its mass number because it is written top of the element. So potassium, if you look it in the periodic table, you will find that it has the atomic number of 19. So it should have 19 protons. So you know the drill now. To identify number of neutrons, you will subtract the number of protons, the atomic number, from the mass number. So 41 minus 19 is going to be 22 neutrons. So potassium is neutral, so it should have similar number of electrons to protons. So it will have 19 electrons. All right. So it said last problem D, carbon 14. So whenever it said like that, an element with just a number, it is just referring to the mass number next to the element. So carbon has element symbol of C in the periodic table. If you look for it in the periodic table, you will find that it will have the atomic number of 6, which means it is going to have 6 protons. If it is going to have 6 protons, and if it has a mass number of 14, the number of neutrons is going to be 14 minus 6. So it is going to have 8 neutrons. And if it has 6 protons, naturally it should have similar number of electrons. So it will have 6 electrons. That's all you need to know about how to identify mass number and number of protons, number of electrons, and number of neutrons for different styles of elemental representation. This is all for this part. I will see you again in the next part.